All right, today we're going to talk about corporate VPNs. We're going to demystify the technology that makes them tick, really pull back the curtain on those secure connections we all rely on every single day. So let's dive in and take a look inside.
You know the drill, right? You click a button, a little icon turns green, and bam, you're on the network. It feels so simple, kind of like this magic secure pipe that goes straight to the office. But what is that pipe really made of? And just how secure is it? Well, as we're about to see, there is a lot more going on under the hood than you probably think.
And understanding what's actually happening inside that tunnel is more important than ever. Because that digital connection we trust so much, well, it's become a huge target for attackers.
Just look at this number, 45%. Let that sink in for a second. According to a 2023 Zscaler report, nearly half of all organizations were attacked through their VPNs in just the last year. I mean, that's staggering, and it's because they're so widely used that they've become this massive flashing target for hackers.
And here's the thing. Attackers have a playbook. They're not always trying to, blow up the walls of the tunnel itself. It's often much simpler than that. They're looking for the unlocked front door, exploiting weak authentication, like stolen passwords, or just finding unpatched software flaws. It's like they're just walking right in. And that is exactly why we need to understand the tech underneath. It's the only way to build a real defense.
Okay, so let's start peeling back those layers. When we're talking about a typical corporate site-to-site VPN, we're almost always talking about two key protocols working hand in hand, IPsec and GRE.
The best way to get your head around these two is with a simple analogy. Think of IPsec as the armored car. Its entire job is security, right? It's there to provide powerful encryption and authentication to protect everything inside. Now, GRE is like the superhighway that the armored car drives on. It's a really versatile tunneling protocol that can carry all sorts of traffic that IPsec alone just can't handle. Things like multicast messages that routing protocols need to talk to each other.
So, to get a bit more formal, GRE stands for Generic Routing Encapsulation. And that word generic is really the key here. Its biggest advantage is its incredible flexibility. I mean, it can pretty much wrap up any kind of network traffic and just send it on its way over a standard IP network.
This really gets to the heart of it. Someone on Reddit actually explained it perfectly. They said to think of a GRE tunnel as just pretending there's a virtual cable connecting two networks that are far apart. All it does is create that connection, that pathway.
But, and this is a huge but, there's a catch. GRE builds the superhighway, sure, but it doesn't build any walls or post any guards. By itself, GRE offers absolutely zero encryption, nothing. All that traffic is just flying down the highway in the open for anyone to see. So to make that highway secure, we need to put our armored car on it. And that, of course, is IPsec. All right, so let's dig into how IPsec actually builds that security. It's not some one-size-fits-all thing. It actually has a kind of blueprint with two very different ways of protecting our data.
So, IPsec, that's Internet Protocol Security, is basically a whole suite of protocols designed to do two really important things. First, authenticate that the data is really from who it says it's from. And second, encrypt that data so nobody else can read it. It's pretty much the industry standard for locking down communications at the network level.
And this is where things get really interesting. IPsec doesn't just have one way of doing its job. It has two completely different strategies for protecting our data packets. We've got tunnel mode and transport mode. And believe me, the choice between them makes a huge difference for both security and performance.
Okay, let's dive into this tale of two packets. How do these two modes actually work, and what do they really protect?
First up, we've got tunnel mode. The best way to picture this is to think about sending a letter. In tunnel mode, you take your entire original letter, I'm talking the letter itself, plus the original envelope with the to and from addresses, and you lock the whole thing inside a brand new, completely opaque armored box. Then you slap a totally new shipping label on the outside of that box. The original addresses? Totally hidden. No one can see them. This is what you typically use to connect entire networks, say from one office router to another.
Okay, now let's compare that to transport mode. It's a totally different approach. Using our letter analogy, this time you just take the contents of your letter, the pages inside, and you seal them in a clear, tamper-proof security sleeve, so the message itself is encrypted and secure. But then you put that sleeve back into the original envelope. This means the original to and from addresses are still totally visible to anyone who handles the mail. The data is protected, yeah, but the routing info is out in the open. This is more common for host-to-host communication, like from your computer directly to a specific server.
So this all leads to a really crucial trade-off. Tunnel mode protects everything, which is great, but that extra armored box adds weight, right? It adds about 76 bytes of overhead to every packet. Transport mode, on the other hand, is lighter, only adding about 56 bytes, because it's just protecting the payload. Now you might be thinking, a 20-byte difference, who cares? But trust me, when you're talking about millions and millions of packets, that adds up and has a very real impact on performance.
Look, I know this can all seem super technical, maybe a little in the weeds, but understanding these details is absolutely fundamental if you want to build real enterprise security that's more than just, flipping a switch and hoping for the best.
So you might be asking yourself, so what? Why should a CISO or anyone on the security team really care about 20 bytes of packet overhead? Isn't that just a problem for the network engineers to worry about? Well, the answer is a big no. It's not really about the 20 bytes. It's about a bigger idea. Recognizing that your VPN isn't some single magic shield. It's a complex system with different layers, and if one of those layers fails, it can make all the other layers completely useless. I mean, think about it. You can have the most perfectly configured AES-256 encrypted IPsec tunnel in the entire world, but it's totally useless if an attacker just steals valid credentials and waltzes right in the front door. We just saw a huge example of this with the United Health Group attack. It was linked to compromised credentials on a remote access app that reportedly didn't even have multi-factor authentication enabled. You see, strong authentication isn't separate from the tunnel. It's the gatekeeper to the tunnel, which is why the best practice, always, is to use phishing-resistant MFA.
So if there's one thing to take away from all this, it's that your VPN isn't just a single wall. It's a layered defense system. It starts with the encryption mode you choose and goes all the way to the authentication that guards the very entrance. And that really leaves us with one final, crucial question to think about. Are you absolutely sure you've secured every single layer?